The bell, as a unit, has an interesting history rooted in the early days of telegraphy and telephony. Initially, it wasn't a measure of sound, but rather a unit of electrical resistance. In 1881, a glossary of terms used in telegraphy and telephony by Latimer Clark and Robert Sabine indicates that Mr. Latimer Clark suggested the name Bell in honor of Professor Bell, recognizing Alexander Graham Bell's work in determining its value. Then in 1882, J.A. Fleming discussed a definition of the volt and mentions that the unit of resistance is the bell, which is defined by the resistance of 1 mile of British standard gauge iron wire. This definition ties the bell directly to a physical property, the resistance of a specific length of wire. The subsequent evolution of the bell unit saw its application shift over time. In the early 20th century, the bell was frequently used as a measure of loudness within telephone systems. Then, in the 1920s, the decibel, abbreviated dB, was introduced as a logarithmic measure of power ratio. The decibel ultimately became the preferred unit for measuring sound intensity. Today, the bell unit is rarely used in either electrical or acoustic contexts. Its historical significance lies in its early role as a practical unit for quantifying resistance in the context of telegraph and telephone networks. To delve deeper, you can research the glossary of terms used in telegraphy and telephony by Latimer Clark and Robert Sabine, available on Google Books, to see the original context of the bell definition. You may also find information regarding the volt by J.A. Fleming. Furthermore, the Wikipedia article on the bell unit can provide more information on its transformation from an electrical unit to its association with sound measurement. The information, though, does focus on resistance of a specific standard gauge of wire. Resistance is a fundamental property of electrical circuits that opposes the flow of current. It's measured in ohms, symbolized by the Greek letter omega. The resistance of a wire depends on several factors, including its material, length, and cross-sectional area. Longer wires have higher resistance, and thinner wires also have higher resistance. The material the wire is made from also plays a crucial role. Some materials, like copper and silver, are excellent conductors with low resistance, while others, like iron, have higher resistance. The concept of a standard gauge for wire is important because it provides a consistent reference point for measuring and comparing wire sizes. Wire gauge is a numerical designation that indicates the diameter of the wire. In the British standard gauge system, which was referenced in the definition of the bell, different numbers correspond to different wire diameters. A lower gauge number indicates a thicker wire, while a higher gauge number indicates a thinner wire. This is in contrast to the American wire gauge (AUG) system, where the relationship is inverse, meaning that a higher number corresponds to a thinner wire. The resistance of 1 mile of British standard gauge iron wire would have been a practical standard for early telephone and telegraph engineers. It provided a tangible, reproducible unit for measuring and comparing the resistance of different circuits and components. It's important to note that the resistance of a wire also varies with temperature. As the temperature of a wire increases, its resistance typically increases as well. This is because the increased thermal energy causes the atoms in the wire to vibrate more, making it more difficult for electrons to flow freely. When using the bell unit, as defined by the resistance of 1 mile of British standard gauge iron wire, it would have been necessary to specify the temperature at which the measurement was taken to ensure accurate and consistent results. The evolution of electrical units reflects the increasing sophistication of electrical technology and measurement techniques. As technology advanced, more precise and convenient units were developed to replace earlier, less standardized units like the bell. The ohm, which is the standard unit of resistance in the International System of Units (C), is defined in terms of fundamental physical constants, making it more accurate and reproducible than the bell. The decibel, which replaced the bell as a measure of loudness, is a logarithmic unit that expresses the ratio of two power levels. This is useful for measuring sound intensity because the human ear perceives loudness on a logarithmic scale. A small change in decibels corresponds to a large change in sound intensity. For example, a 10 decibel increase represents a tenfold increase in sound intensity. The decibel is also widely used in other fields, such as electronics and telecommunications, to measure signal strength and noise levels. The concept of grounding, which is mentioned in relation to Mike Holt's research, is an essential safety measure in electrical systems. Grounding provides a low-resistance path for fault currents to flow back to the source, which helps to protect people and equipment from electrical shock and damage. A properly grounded electrical system ensures that if a fault occurs, such as a short circuit, the fault current will quickly trip a circuit breaker or fuse, cutting off the power to the circuit and preventing a dangerous buildup of voltage. Grounding systems typically consist of a grounding electrode, such as a metal rod or plate buried in the earth, and a grounding conductor, which connects the grounding electrode to the electrical system. The grounding conductor must be sized according to the requirements of the National Electrical Code, NEC, to ensure that it can safely carry the maximum fault current that is likely to occur. In addition to providing a path for fault currents, grounding also helps to stabilize the voltage of the electrical system and reduce electrical noise. A well-grounded system can improve the performance and reliability of sensitive electronic equipment. There are different types of grounding systems, each with its own advantages and disadvantages. Some common types of grounding systems include solidly grounded systems, impedance-grounded systems, and ungrounded systems. Solidly grounded systems are the most common type and are used in most residential and commercial buildings. In a solidly grounded system, the neutral conductor of the electrical system is directly connected to the grounding electrode. Impedance-grounded systems use a resistor or inductor to limit the amount of fault current that can flow to ground. This can help to reduce the risk of arc flash, which is a dangerous electrical explosion that can occur when a high-voltage fault occurs in an air-filled enclosure. Ungrounded systems do not have a direct connection to ground. While they can offer some advantages in terms of reliability, they are generally not recommended for use in most applications due to the increased risk of electrical shock. The National Electrical Code, NEC, provides detailed requirements for grounding electrical systems. These requirements are designed to ensure the safety of people and property. The NEC specifies the types of grounding electrodes that are permitted, the size of the grounding conductors, and the methods for bonding different parts of the electrical system together. It is important for electrical contractors and engineers to be familiar with the NEC requirements for grounding to ensure that electrical systems are installed and maintained safely. The historical context of electrical units like the bell helps to illustrate the evolution of electrical technology and the importance of standardization. Standardized units provide a common language for engineers and technicians to communicate and collaborate effectively. They also ensure that electrical equipment and systems are compatible and can be safely interconnected. The development of the ohm, volt, amp, and other standard electrical units has been essential to the progress of electrical engineering and the widespread adoption of electrical technology. These units are based on fundamental physical principles and are defined in terms of reproducible standards, ensuring their accuracy and reliability. As technology continues to advance, new units and standards may be developed to meet the needs of emerging applications. For example, the increasing use of renewable energy sources, such as solar and wind power, has led to the development of new standards for grid interconnection and power quality. These standards are designed to ensure the safe and reliable integration of renewable energy into the electrical grid. The study of the history of electrical units can provide valuable insights into the evolution of electrical technology and the importance of standardization. It can also help to appreciate the contributions of the many scientists and engineers who have shaped the field of electrical engineering. The journey of electrical units from the bell to the ohm demonstrates the ongoing process of refinement and improvement in the quest for accurate and reliable measurement. The bell's connection to telephone wire highlights the practical origins of many electrical concepts. Electrical resistance, as the bell initially measured, is the opposition to the flow of electric current in a circuit. It is analogous to friction in mechanics. The higher the resistance, the less current flows for a given voltage. Resistance is measured in ohms. 1 ohm is defined as the resistance that will allow 1 amp of current to flow when a voltage of 1 volt is applied across it. The relationship between voltage, current, and resistance is described by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. This is one of the most fundamental laws in electrical engineering. The resistance of a conductor depends on its material, length, cross-sectional area, and temperature. Different materials have different resistivities, which is a measure of how strongly they resist the flow of current. Copper and aluminum are commonly used as conductors because they have low resistivities. Longer conductors have higher resistance, and thinner conductors have higher resistance. The resistance of a conductor also increases with temperature. Insulators are materials that have very high resistivities and are used to prevent current from flowing where it is not wanted. Examples of insulators include rubber, plastic, and glass. The concept of resistance is essential for understanding how electrical circuits work. Resistors are components that are specifically designed to provide a certain amount of resistance in a circuit. They are used to control the flow of current, divide voltage, and provide other functions. Resistors are available in a wide range of values and power ratings. The power rating of a resistor indicates how much power it can dissipate without overheating. The color code on a resistor indicates its resistance value and tolerance. The tolerance is the percentage by which the actual resistance value may vary from the indicated value. The Bell unit's historical connection to the resistance of a specific length of wire highlights the importance of having standardized units of measurement. Standardized units allow engineers and technicians to communicate and collaborate effectively, and they ensure that electrical equipment and systems are compatible. The International System of Units (SI) is the internationally recognized system of units for scientific and technical measurements. The SI system includes the ohm as the unit of resistance, the volt as the unit of voltage, the amp as the unit of current, and the watt as the unit of power. The use of standardized units has been essential for the advancement of electrical engineering and the development of modern technology. The evolution of the Bell unit from a measure of resistance to a measure of loudness demonstrates how the meaning and application of units can change over time. The decibel, which replaced the bell as a measure of loudness, is a logarithmic unit that expresses the ratio of two power levels. The decibel is widely used in acoustics, electronics, and telecommunications. The decibel scale is logarithmic because the human ear perceives loudness on a logarithmic scale. A small change in decibels corresponds to a large change in sound intensity. A decibel is a dimensionless unit, meaning that it does not have any physical dimensions. It is defined as 10 times the base minus 10 logarithm of the ratio of two power levels. The reference power level is typically 1 milliwatt for acoustic measurements and 1 microwatt for electrical measurements. The decibel is a convenient unit for measuring sound intensity because it allows for a wide range of sound intensities to be expressed on a relatively small scale. The threshold of hearing is typically around 0 decibels, while the threshold of pain is around 120 decibels. The decibel is also used to measure signal strength in electronic circuits. The signal-to-noise ratio, SNR, is a measure of the strength of a signal relative to the background noise. It is typically expressed in decibels. A higher signal-to-noise ratio indicates a stronger signal and less noise. The decibel is a versatile unit that is used in a wide range of applications. Its logarithmic nature makes it particularly well suited for measuring quantities that vary over a wide range, such as sound intensity and signal strength. The Bell unit's legacy lives on in the decibel, which is a testament to the enduring impact of Alexander Graham Bell's contributions to science and technology. The information provided helps one understand the historical context and evolution of electrical units.